Hi class, next topic natin sa geosynthetics are the geonets. So we've defined this before and then you've showed the advantages, disadvantages, mga major functions niya. And then nasabi na din natin na it is somewhere in between geogrid and geotextiles. So, kumpara kay geogrid, mas maliliit na yung apertures or opening ni geonets. And kumpara kay geotextile, mas malaki ang opening ni geonet kay geotextile. So, that's physically, yun yung relationship nila physically. But by function, si geonet, ang main function niya is sa drainage. So, let's discuss first yung mga physical properties ni geonets. So other properties are mechanical, endurance, environmental, hydraulic properties. So physical properties, the primary function of geonets is drainage. They are specialized design consisting of intersecting ribs that create a net-like structure, makes them highly efficient for facilitating the flow of fluids such as water or gas in civil engineering and environmental applications. So, why drainage yung primary use niya? So, efficient siya sa fluid flow. Geonets are specifically engineered to provide high flow rates under pressure, making them ideal for draining water or venting gases. So, prevention of hydrostatic pressure. By allowing water to flow through them, geonets prevent the buildup of hydrostatic pressure, which can compromise the stability of structures like retaining walls, landfills, or tunnels. And also, geonets have lightweight and durable. Unlike traditional gravel drainage system, geonets are lightweight, easy to install, and resistant to clogging, which enhances their efficiency in draining fluids over the long time. So, kumpara do sa mga naunang materials natin to form drainage, ito yung mga advantages ni geonets kumpara sa kanila. Mas efficient siya nga sa fluid flow, prevents hydrostatic pressure kasi nga maganda yung drainage capacity niya. And of course, kumpara naman sa mga gravel natin dati, very lightweight siya. And due to lightweight siya, easy siya sa installation. So, also, let me add, durable siya kasi, of course, it's made of plastic. So, hindi siya nade-degrade that easy. Key applications utilizing drainage function. So, ito yung mga situations where geonets are used for drainage. Sa example, sa landfill, geonets are commonly used for leachate collection systems where they drain harmful liquids that accumulate within the landfill. So, for example, meron tayong landfill. So, madaming syempre mga basura yan. Basura, they can secrete mga harmful chemicals na yung harmful chemicals na yon, it should not penetrate sa ground natin, di ba? That's why we put drainage system sa ilalim sa pinakailalim sa base ng landfill, and then lalagyan pa na that is to contain yung chemicals and also para ma-drain sila properly at hindi mapunta sa ground. So that is by use of geonets, and of course in combination of other geosynthetics like yung geomembrane that will contain the liquid that will definitely separate niya yung mga dumi from our soil, and then you use siya together with the geonets kasi nga the geonet will do the drainage function. Number 2, retaining walls. They help drain water from behind the retaining walls. Yung mga lupa behind the retaining walls. So, i-collect, i-drain yan ng geonets natin. So, for example, this is our retaining wall. Siyempre, may lining yan. Then, meron yung geosynthetics dito, geogrid or geotextile. And then, pwedeng maglagay ng geonet dito for drainage din. Or dito na lang sa pinakailalim din. And then, magkakaroon ng canal or doon or dito para sa drainage. Then, number 3, tunnels and basements. So, geonets are used for Geonets are used for groundwater drainage behind tunnel linings and basement walls to prevent seepage. So, may mga tunnels tayo, like yung mga train tunnels natin. So, syempre, soil above yan. So, parang yung example natin sa quiz dati, laliningan yan ng geomembrane, and then you can also add yung geonet to drain yung water, and then you will have a collecting system dito. Pwede ka magkaroon ng pipes or culverts, etc. Number 4, green roofs, serving as a drainage layer to prevent water clogging while promoting healthy plant growth. Thus, while geonets may be used in a variety of ways, their primary and most common function is drainage, especially in projects where efficient fluid management is essential. So, buildings na may green roof, syempre may soil pa din doon, may soil dyan. So, to prevent clogging and syempre pagkasira ng roof, you need good management ng water. So, you can line it with geonet here para makollect mo siya dito. You can have a gutter doon. So, next, our types of geonets. So, we have the biplanar geonet. Biplanar, ibig sabihin, dalawa yung grid lines niya. Ganyan. Consisting of solid extruded rib. So, ibig sabihin nito, yung ribs niya are solid. Ito, solid sila. So, these are the most common type of geonets. Number 2, we have the biplanar geonets. Biplanar then, and with foam extruded ribs. So, makikita nyo, foam yung, may pagka-foamy yung niya, yung ribs niya. And then number 3, triplanar, and then solid yung ribs niya. So, triplanar, as you can see, grade 1, grade 2, and then grade 3. So, kaya triplanar, and then solid yung ribs niya. So, physical properties, density or specific gravity. Siyempre, meron tayong mga standard organization, yung ASTM and yung ISO, mga standardization organization sila. And they set yung mga physical properties of our materials. So, ang standard nila for geonets, the density or specific gravity ng geonet should be at least 0.005 milligram per liter. And then thickness, ang thickness niya should kakayanin yung 50 kilopascals. And then mass per unit area, ito siya, for a 5 mm thick na geonet. So, next, mechanical properties niya. So, mechanical, ito yung mga performing characteristic niya. So, performance in tensile strength, performance under tensile stress, and elongation. So, syempre, ang mga materials natin tinetest. And for geonets, tinetest yung kanyang tensile strength. So, based sa, though hindi as in ginagamit yung tensile stress niya kasi hindi mo naman, kapag ginamit mo siya, di ba usually nga sa drainage siya, you don't need yung tensile capacity ng geonets for tensile stress. But still, we have tested yung geonets for tensile strength, and it showed na yung machine direction daw ng Geonet have higher capacity kumpara dun sa cross-line direction. So, what does yung machine direction? Ito yung machine direction. So, yung mga ribs along this line, yun yung mas malakas kaysa kapag itong mga cross machine direction na to. So, ibig sabihin, drawing natin to. Kunwari, ito yung biplanar geonet natin. Ito yung machine direction, diba? Ito yung cross machine. So, ibig sabihin machine direction, ito yung mahabang part niya. Tapos nakarolyo siyang ganyan, as you can see dito sa illustration. So, mas mataas yung tensile strength dito kesa dun sa tensile strength dito. Mas minimum to, dito mas maximum. So, ano ang ma-help nito sa paggamit ng mga geonet? Though hindi ginagamit yung tensile strength na yun, if it is better to lay, kapag nilatag mo yung geonet mo, better lay it along the machine direction. Like ito, nilay niyang paganyan, kasi malamang ang flow ng drainage niya is along this direction. So, mas malakas yung direction na to dahil ito yung machine direction. Kaya, better use the machine direction along the flow para mas malakas siya doon. Next, compressive strength and deformation. The compressive strength is very important because of the influence of the compressive deformation or collapse has on the ability of the geonet to conduct liquid within its planar structure. The biplanar solid rib and biplanar foam rib begin to deform at normal stresses between 600 and 850 kilopascal, and there is a laydown or rollover tendency. This occurs because the parallel sets of ribs making up the respective geonets are not exactly perpendicular to one another at the junctions. So, compressive strength is important sa mga geonets kasi their application is, it requires compressive strength. Example for landfills, of course, ayun nga, may mga bulk waste tayo dyan, mabibigat, tapos, very irregularly shaped. Pag niliningan mo yan ng geonet, ano yung strength in question natin? It is the compression ng geonet natin. So, ito nga yung standard na compressive strength ng ating geonet. So, sabi niya, mas malakas, yung solid rib na triplanar has still the higher flow rate and capacity. It also shows no inflection point since the central and thicker set of ribs is perpendicular to the normal stress. Thus, its response to normal stress increases with compressive strain in direct proportion to the density of the resin. So, sabi nga dito, yung biplanar na solid rib and biplanar na foam rib, mas weaker sila in terms of compression kumpara kay triplanar solid rib na geonets. Also, mas magaling pa rin si triplanar in terms of flow rate. So, bakit daw mas malakas si triplanar solid rib? Kasi mas perpendicular yung mga ribs niya dun sa point of intersection nila, sa ganyan. Kumpara dun sa mga biplanar na solid rib, hindi siya perpendicular dun sa junction nila. Hindi perpendicular. So, nagkakaroon ng rollover tendency. So, balikan nga natin ano yun. So, kung makikita nyo dito, hindi sila perpendicular. Ito. So, it can roll pag ganoon. Kasi parang kung circular siyang ganyan, hindi siya perpendicular, it can roll daw pag ganun. So, ayun. Ito kasi yung ribs niya parang pag ganoon Parang medyo pag ganun, hindi siya. So, ganun yung pagkakali ng Geonet na biplanar, solid, and foam rib. Kumpara kay triplanar, mas thick pa yung junction ni triplanar eh. So, mas malakas ang compressive niya talaga. So, these are the tests conducted. Comparing yung tatlo, if this is yung para kay foamed rib biplanar, this one is kay biplanar na solid, and this is kay triplanar na solid rib. So makikita na mas superior talaga si triplanar, mas mababa si foamed rib na biplanar. Okay. So sa shear strength naman, the shear stress along the plane within its own thickness is not felt much of a problem for the currently available utilized geonets. Considerably more concern should be focused on the interface friction behavior with respect to the materials above and beneath the geonet. So, geonets, of course, placed yan sa soil, between soil. So, may soil dito and may soil doon. So, yung type of soil mo can be very high in friction. Kunwari, bato-bato ka, malalaki ang granules mo, high in friction ka. So, yun daw ang more concern sa mga geonet. That's why we line yung surfaces ng geonet with geomembrane or geotextiles. Ito. So, this is particularly the case for the geonet composites with a covering geotextile. Due to the relatively low shear strength of geotextile to geonet, it is common practice to bond the geotextile to the geonet at the manufacturer's facility. So, pwedeng lagyan mo ng geotextile dito and then another geotextile doon. GTX or GTX, or sometimes combination ng meron kang GTX dito, geomembrane dito, or geomembrane dito, geomembrane doon. So, it depends dun sa paggagamitan. Kunwari ka sa landfill ulit, landfill. So, syempre, waste nga yan. Ayaw natin pumunta sa soil yan. So, ang pang-line mo ng geonet mo is geomembrane. Kasi geomembrane, this can really contain yung fluid. Hindi magsisip kay geomembrane talaga yan. Eh, si geotextile, may butas-butas pa din yan. Kahit sobrang maliliit. So, kailan gagamitin si geotextile? Kunwari, for non-toxic na, kung yung fluid na i-drain mo is non-toxic naman. Kumbaga, pwede siyang mag-protrude or mag-seep doon sa soil. Like, mga simple drainage system like, yun, retaining walls. So, pwede mong i-line ng geonet, and then geonet dito. And then, ano ba to? Kapag mataas yung friction mo dito, you can line them with geotextile. GTX ka na. Kasi, kumpara sa ito, GM, kasi ang i-contain mo harmful chemicals. But dito, tubig lang naman, so you can use geotextile na lang. Kasi pwede namang mag-sip yung excess na water na hindi mo totally na-drain. So, yan. Next, endurance properties ni geonets. Endurance properties of concern when using geonets have to do with the long-term sustained deformation of the material and its ability to continue to transmit the required in-plane flow rate. The four issues are relevant. So, number 1, paano na kukuha ang endurance properties ng geonets? Through the type of polyethylene resin, yung type of plastic na ginagamit. The high density resins will result in relatively high modulus, high strength, and high creep resistance. Okay, yeah, so the type of plastic. Number 2, creep behavior of the geonet structure. Sustained load or creep is the reduction in thickness of a geonet under applied compressive stress. Here, the density of the resin type of structure and the composition of the rib junctions are all significant. So, to get yung good creep behavior, sabi nga, you need to have density. So, to get yung a good creep behavior, so that will be dependent sa density ng plastic na gagamitin mo and yung type of junction nung geonet mo. Yung mga intersection niya, those are the junctions. Number 3, intrusion of the adjacent materials into the geonet's apertures. All geonets will necessarily be covered on the upper and lower surfaces with geotextile geomembrane concrete wall surface or some other material. If the geonet surface are not covered, the soil will invade its apertures, rendering flow impossible. Intrusions refer to the deformation of the flexible covering material, primarily geotextile, occupying some of the geonet's void space. So, explain that, diba nga, ang geonet natin para siyang net. So, we provide on both surfaces a covering daw. You can use geotextile or geomembrane sa top and bottom niyan. Let's have a cross-section. So, this is the geonet. So, you can have a covering daw, top and bottom, geomembrane or geotextile. So, that is also to prevent yung mga soil na pumunta dito sa opening ng geonet natin. Kasi kapag na-cover yun, malelesen yung drainage capabilities niya. So, number 4, the possible extrusion of clay through a covering geotextile. If a compacted clay liner or a geosynthetic clay liner with bentonite is placed adjacent to a geonet composite, there is a possibility of the clay particles extruding through the geotextile's void into the geonet. Conversely, non-woven geotextiles have generally been effective in preventing soil extrusion. So, soil extrusion, so pwede silang mag-poke out and then cover yung apertures ng what we call this geonet natin. So, these are yung mga intrusions that could happen dun sa geonet natin. So, as you can see dito, ito yung geonet natin, may covering siya ng geomembrane top, geomembrane at bottom. So, lesser intrusion siya. Ito kasi yung opening, yung aperture. So, dito, may soil, may geotextile, and then geomembrane. There is more intrusion kapag geotextile ang ginagamit kumpara kay geomembrane. And then, as you can see, third, needle punch geotextile, and then, ayun. Mas malaki ang intrusion ng geotextile sa geonet kapag yung needle punch geotextile ang gagamitin kumpara sa sa heat bonded geotextile. Okay? So, kapag nako-cover ito yung opening ng geonet eh. Pag na-cover yan, mas mahihirapan mag-flow ang water dito. Diba may sinircle ako kanina? In-plane flow rate. Yan yung, ganyan mag-provide ng drainage yung geonet through its in-plane surface. Ganito mag-flow yung water sa geonet. So, kapag na-cover yan, like ito, na-cover yung aperture na yun, mahihirapan lalong mag-flow yung water dito. Lalo na pa dito. Half ng geonet is na-cover niya. So, isa yan sa mga mga items na kailangan those are the items na kailangang i-consider kapag nagde-design tayo. Number 4, environmental properties ng geonets. Number 1, temperature. Under high temperatures, flow rates increase over standardized laboratory test conditions. The converse or in kabaliktaran, kapag cold temperature naman, it decreases yung flow rate sa yung flow rate ng geonet natin. Perhaps more important is that the creep of polymers increases under increasing temperature. So load resistance creep increases under increasing temperature. So also kapag increasing temperature mas malaki yung hindi nagko-contract yung material. Number 2, nature of liquid being transmitted. If chemicals or leachate are being transmitted, a number of questions arise. One of these is the chemical resistance of the polymers being used for the geonet and the covering geotextile or the geomembrane to the site-specific liquid. And then biological growth within the geonet. In most transportation-related systems, such as roads and walls, the problem does not appear to be too serious. In systems related to waste containment, the issue should be addressed. At the bottom of the landfill, temperatures can be high. Ample organic material as a biological food source is available. So, bacteria and fungi could thrive. Pwedeng mag-live yung bacteria doon. Whether oxygen is available or not only dictates whether aero or anaerobic conditions prevail. Still, merong bacteria and fungi na pwede pa rin mag-live doon kasi nga meron silang pagkain. Procedurally, we must use high flow rate factor of safety we must use a high flow rate factor of safety or have systems designed so that flushing is possible. You need higher FS daw. So, FS natin can be 1.5 hanggang 3 or greater is of course better, di ba? It is not usual to use 1.5, so 2 to 3 or up. So resistance to light and weather. It is not felt to be a serious concern for most situations. Polyethylene is quite resistant to weather-related degradation, and carbon black is included in placement. For geotextile covered geonets, the situation is controlled by the ultraviolet degradation of geotextile. So, ito yung iba't ibang chemical or environmental related na situations pwedeng ma-undergo yung geonet natin. So, for these different situations, our geonets may natetest naman, may capacity sila kontra sa mga to. And of course, by factor of safety, increase natin yung factor of safety para mas durable yung ating geonet or yung geosynthetic system na gagamitin for different situations like landfills or sa roads or retaining walls. Number 5, ito yung pinaka-importanting property, hydraulic property ng geonet dahil ito nga yung primary usage niya which is drainage. So let's have this video first.
Hi, we're here at the Geosynthetic Institute in Folsom, Pennsylvania. Take a look at ASTM D as in David 4716 for transmissivity and plane flow characteristics of geocomposites, geonets, geospacers. These materials typically consist of a core and a textile. The textile is typically bonded to the core. The textile is used as a filter. The core, or the spacer, is used for transmission textile, water filters through the geotextile, and then subsequently moves in plane through the core or the spacer. This is the unit, the transmissivity unit. It's broken down into three parts. It has an upstream reservoir, a normal pressure where the specimen is housed, and then the outlet works downstream. The geosynthetic is typically placed inside of the holder. It is a specimen. The specimen is typically 300 millimeters by 300 millimeters. It's typically a little long, 25 millimeters on each side, so that you can push it into the upstream reservoir and subsequently the downstream outlet works. Critically important not to have any air in the interstices of the spacer or the net, so therefore you place typically a plexiglass lid over top of it. Then you're going to need some sort of seal. We use a closed cell foam for this particular case, so that we don't have any leakage around the perimeter of the holder. And then a big pressure plate so that we can apply the normal pressure. Subsequent to that, we have to place a load cell, and then we load the system up to the prescribed normal pressure. In this test, you typically have 3 normal pressures and 3 gradients, which are prescribed by the owner. So you pressure is applied, you should notice that you have 3 types of creep here. You actually have compression or consolidation of the overlying soil. You have a tension creep of the textile into the interstices of the net. And you also might have compression of the core itself. You'd like to induce flow, and that flow is induced typically by pumps underneath the equipment. This is how we control the head, which controls the gradient. The gradient is actually the head divided by the length of the specimen. You do that by increasing the rheostat, and that controls the pump, the velocity of water out of the pump. And you can see that we arrive at the head. You can fine tune it so you don't make a lot of turbulence at the top. The gross change in the head, though, the pipe, and then you can change the elevation of the pipe, as you can see. And this is an overflow pipe and allowing different head. Here is a very high hydraulic tank with gradient increase. You can see quite rapidly that we will change the head by dropping into position. And that's how the head is controlled. The gradients are anything from 1, which would be a vertical wall, to somewhere around 1 to 2%, and that's our typical 2% is a bottom grade for a landfill. You can see the inlet water is flowing through the specimen in plane, and then flows out at the end. You typically monitor this by a bucket or graduated cylinder and a stopwatch. You're looking at flow rate with respect to time. Obviously, the higher the flow, the bigger the bucket you'll need. Sometimes we close off this bucket with a valve and subsequently collect that with respect to time. You control the gradient typically off of manometers. This is the one for the outlet, and this is similar one for the inlet. You have to make sure that there are no air bubbles in the lines, so that you get an accurate reading with the manometers. For very low gradients, typically use a pressure transducer. This pressure transducer is strapped across the back here. We control the gradients off this monitor. It's hydraulic and about 0.1. And now apply a press normal press, ever increasing. You see the flow rate is pretty consistent now, but we should wait 15 minutes for the flow rate. We use a stopwatch and then graduate the cylinder or this particular flow rate. We have to increase the volume. This is air, there's no weight, and we put weight in. But here you have a pretty consistent flow rate through this. And I'll show you by increasing the normal pressure, this flow rate will decrease. What we're doing is that pressure corridor with respect to time. You feel the flow rate decreasing. You see the flow rate has slowed significantly. And basically we crush the corridor with respect to time. This is ASTM David 4716 transmissivity. You need to have 3 gradients and 3 normal pressures to get the toner curve, which you'll see close up in the subsequent slides. And we'll certainly show you the calculations. You do have to see the temperature of the water and try to maintain that as close to 20 degrees C. In addition to this, we'd like to show you an internal reference material. This material is what we use for the reference board. We can get flow rate through this consistently, and this is our IRM or internal reference material, which we use for repeatability in our lab. So this is transmissivity in plane flow. You will see a radial flow device in the subsequent slides, which is ASTM 6570.
Okay, so napakita niya yung paano ginagawa yung transmissivity test. So, the flow rate or transmissivity of Geonets is performed by the in-plane hydraulic test, which is ASTM D4716 or ISO 12958. From the test data, this one, so transmissivity value can be calculated. Transmissivity is a key concept in hydrogeology that refers to the ability of an aquifer to transmit groundwater through its entire saturated thickness. It is essentially the measure of how much water can flow horizontally through an aquifer. Thus, geonets can handle large flow rates compared with soil only, due to the higher velocity of flow within the significantly larger voids. Furthermore, the machine direction flow rate in triplanar geonets is even higher than in biplanar geonets, as we've said a while ago. So, for example, a 300 mm of sand alone, having permeability coefficient of 0.1 cm per second at a hydraulic gradient of 1, can only carry 0.018 cubic meter per minute in meter length. So, hydraulic gradient is the rate of change in total head or yung pressure per unit distance in flow in a particular direction. So, transmissivity, yun nga yung yung measure of how much water can flow horizontally. Kaya itong transmissivity test, makikita nyo, horizontal ang flow ng ating tubig. Kasi that's how we drain water naman, no? So, si Geonet, hindi pag ginamit mo siya sa drainage, kunwari ito yung water, hindi mo naman siya ilalay na ganyan porque nandito yung opening niya. Ganon yung hindi mo siya ganon itatayo or i-install. So, Geonet provides drainage by its planar direction. Dahil meron siyang mga, yung mga butas, meron siyang mga apertures. Because of that apertures, may void siya. So, by providing ng voids dun sa depth of soil mo, kunwari may soil ka, since geonet have apertures, pag nag-insert ka ng geonet dyan, may corresponding thickness pa din naman ang geonet. So, may butas siya dito, butas dyan. So, it provides a way through those voids. Meron path na drainage path ang tubig papunta sa pipe na lang, drainage pipe mo na. So, ganun mag-provide ng drainage si Geonet horizontally. And yung amount of flow that it can provide, that can be measured by itong test nga na to, ASTM D4716, or the transmissivity flow calculation, or yung test na to. So, makikita natin merong water supply, and then dito sa reservoir na to na ko-control yung pressure or yung head, di ba? Head is of course pressure, then corresponding pressure. So, merong pipe dyan, kaya nako-control ang head dito. And then, magfa-flow ang water natin horizontally. Pupunta siya dito sa pinakang main test structure natin dito. So, nandito yung geonet mo and corresponding covering niya. Kung ano ang i-design yung ang pipiliing mga covering, geomembrane man or geotextile, ilalagay sila dito. And then may mga plates dyan, may rubber or foam to prevent leakage upward dito, para hindi mag-leak. And then low-loadan yan. So, di ba kasi kapag kinompress, kunwari soil lang to, you have a set of soil. Kung soil lang yan, tas kinompress mo, pag nakompress yan, it is more difficult for water to flow through, di ba? So, using geonet, ito nga, pag na-compress ang soil dito, supposedly, mas mahirap mag-flow, pero since nag-provide ka ng geonet, nag-provide ka ng drainage, or nag-provide ka ng void, para may way, or may path na, may madadaanan na yung water palabas, at mag-drain na siya. So, yun yung tinetest dito sa geonet, sa experiment na to, sa test setup na to, na under load pressure, under normal pressure, how much flow rate yung kaya ng geonet ilabas. And then, may sinabi ditong hydraulic gradient. That is yung change in total pressure head per unit distance. So, ito yung mga pressure gradient. So, meron tayong pressure gradient, hydraulic gradient. May hydraulic gradient na 1, and then pababa. So, what does mean kapag ang hydraulic gradient mo is 1? Ibig sabihin, mas malakas yung ang outflow ng tubig mo. Kapag pababa ng pababa, ibig sabihin, mas mabagal ang flow, or paglabas ng ng tubig. So, ayun nga, na ko-control ng test na to yung hydraulic gradient. They have instrument and mga measuring tools dyan. So, kapag pina-perform daw ang test na to, kailangan laminar or consistent ang outflow ng tubig mo dito, and they maintain temperature around 20 degrees Celsius. So, kapag nagte-test ng geonet, para malaman yung capacity ng flow niya under pressure, you need to test yung geonet in 3 normal pressure at 3 gradient. 3 gradient at 3 normal pressure para ma-form mo yung curve ng geonet mo. It is a curve, normal stress versus yung flow rate niya. So, for this figure 4.7, ito yung flow rate behavior of a 6.3 mm thick na biplanar geonet sandwiched between 2 1.5 mm HDPE geomembrane. So, ito yung test result niya. So, imbes na tatlong gradient lang, ginawa niyang 6, no? 6 gradient niya. So, gradient 1.5 and then pababa. So, makikita dito, kunwari, for a pressure na, kunwari, nag-apply ka ng 800 kilopascal na pressure, and then, ang gusto mong gradient is 1. So, ano yung corresponding flow rate? Kukuha mo yung flow rate na kaya ng geonet mo. What if 600 na normal stress lang ang mangyayari, tapos gradient lang ay 0.05, makukuha mo yung kayang flow rate ng geonet. So, mataas ang kayang flow rate ng geonet. Ano? Kumpara dito sa, kunwari, meron ka daw 300 mm na sand alone at hydraulic gradient na 1.0, ang flow rate lang kapag sand alone is 0.018 cubic meter per minute per meter length. So, kumpara natin sa pag may geonet dito sa table na to. For a specific geonet setup na geonet with geomembrane taas at baba, ang kaya niya for a gradient na 1, ito yung lowest na kaya niya. Ang flow rate na kaya niya is, sabihin mo nang nasa 0.05 m³ per minute per linear meter. So, mas mataas naman siya, almost, say, 4 times kumpara kay ito, or 3 times kumpara kay kapag soil alone lang. So, mabagal ang drainage kapag soil alone lang, no? So, ayaw natin ng mabagal na drainage or no drainage at all kasi maiimbak yung pressure dun sa system natin, di ba? Kaya gusto natin ng drainage para hindi mataas ang pressure. Now, for this one naman, we have another test setup or another system of geosynthetics. So, for this another material, it is a combination of 6.3 mm thick na geonet, same dito. Pero, ang kanyang covering is non-woven needle punch geotextile sa taas, and then below is geomembrane. So, kumpara natin anong nangyari. So, at pressure, at hydraulic gradient na 1, ang kaya niyang flow rate ay, say, 0.035 m³ per minute per meter length. So, kumpara natin dun dito. Diba, ito at 1, ang kaya niya is 0.05 cubic meter per minute per meter length. So, mas mataas ang kayang i-provide ng ganitong setup or combination of geosynthetics. Mas mataas ang flow rate nito, mas okay siya. But of course, hindi lang naman flow rate ang kino-consider kapag nagde-design tayo ng drainage or ng isang system, madami pa din naman. What if kailangan mo ng protection from extrusion or intrusion? So, di ba nakita natin yung geomembrane is better nga kumpara kay geotextile. So, we have maraming factors. So, to get yung transmissivity value, which is denoted by theta, we have derived this formula, and then per standard, ito yung magandang transmissivity values for landfills or waste pile. Ang transmissivity na magandang value is 3 times 10 raised to negative 5 square meter per second, and then for surface impoundments, ito naman. So, take note of the unit ng transmissivity. It is area per unit time. Kasi nga, transmissivity is a horizontal flow of liquids natin. Ito. That's why I put this one. So, transmissivity is essentially measures how much water can flow horizontally. Kaya ito yung ating unit for transmissivity. So, example. A geonet tested in the laboratory under site-specific conditions results in a flow rate per unit width of 0.65 yan. And at hydraulic gradient na 0.04. So, mababa ang hydraulic gradient. So, question number 1, what is the equivalent transmissivity in units of square meter per second? And number 2, does this value meet the EPA criteria for landfills? So, ito yun. Ano ba yung criteria natin? 3 times 10 negative 5. Ito sa negative 5. Yan. Aha meter per second. Okay. So, we have this, ayaw magsulat. We have this equation from this nakuha natin. So, we can use this one. So, substituting yung mga values, we get yung flow, transmissivity value na ito. And then, compare natin siya dito. Does it meet yung, yung limit? So, since mas mataas tayo sa limit, edi okay siya. And then, computing the factor of safety, it is 54, napakataas. So, okay siya. Okay, number 6, allowable flow rate. So, Geonet design is also designed by function concept. Ibig sabihin, we need to establish yung factor of safety. So, factor of safety nga, it is 1.523 or more. So, we have this general equation for factor of safety, Q allowable, ito yung kaya ng material mo, and then required is yung anong kailangan ng system mo per your design. So, Q allowable is yung ultimate, then multiply mo siya ng several factors. So, for Geonets, ito yung mga factors na kailangan. Nandito sila sa table na to. And then, what do they mean? RFIN is reduction factor for elastic deformation, intrusion, etc. And then RFCR, it is a reduction factor for creep deformation. And then RFCC, reduction factor for chemical. RFBC, reduction factor for biological reasons. But if yung factor of safety is given by ito na, overall na, ito na yung isa na lang ang i-divide mo since overall na ito. So, that is your Q allowable. So, example, what is the allowable Geonet flow rate to be used in the design of a secondary leachate collection system? Assume that laboratory testing at proper design load and proper hydraulic gradient gave a short term between rigid plates value of transmissivity. So, ano ang hinihingi niya? Yung allowable, Q allowable, no? This one. So, we have this formula. So, what is your Q ultimate? Yung kaya ng material mo, which is this one. So, i-multiply mo siya sa mga factors, which you can find dito. So, anong ginamit niya sa RFIN? Since nakadepende ang mga reduction factors sa type of application na gagamitin mo. So, saan ba gagamitin ito? Secondary leachate collection. So, secondary leachate collection nandito. So, ito yung range ng factor of safety na gagamitin. So, anong ginamit niya? So, lahat 1.75. Pero kay, what is this? Ito yung creep, CR, no? Mas mababa ang ginamit niya sa creep. So, that's okay. Within the limit naman siya. So, answer is ito. So, designing geonets for drainage. So, ito pa rin ang formula natin dahil nga design for function tayo, kaya factor of safety. And then we have this formula. So, ayan. So, K, ano ba yung K? Makikita nyo naman dito. Permeability factor, I, hydraulic gradient, area, this area, width times yung thickness. Okay? And then sabi na natin, theta is transmissivity. And then designing geonets for environmental related applications. Geonets are widely used in landfill liner system as function niya as primary leachate function. And then pwede daw siya side or bottom slopes ng landfill. And then as leak detection system between the primary and secondary liners, and they can also be placed above barrier layer in final cover system to drain surface water infiltrating the cover soil. So, ito yung functions ni geonet kapag ginamit siya sa landfill. As such, geonets are placed with either a geomembrane on both sides or geomembrane sa beneath and sa below, and then geotextile above. So, in this latter case, the geotextile, latter case, this one. So, drawing natin muna siya. Ito si geonet. And then, sa taas daw niya is geotextile, GTX. And then, under niya is geomembrane. So, in this latter case, the geotextile has either granular soil or clay soil above. Dito daw. Pwedeng clay. Note that the inverse cross-section is also possible. That is, there is a geomembrane above and a geotextile with soil below. Lastly, the geonet can have geotextiles on both sides, generally for the purpose of enhanced friction against the opposing surfaces of textured membranes. So, ano pa bang masasabi natin dito? Kapag ganyan, ang ang setup ng geosynthetics mo, geotex ka dito, geonet ka dito, geomembrane doon, may soil ka doon, so your leachate can go through the geotex and then magda-drain siya dito sa geonet mo. And then geomembrane, this make sure na kahit may lumampas dito na leachate or yung mga chemicals from your landfill, okay lang kasi geomembrane can handle this. Parang ito ang mas magandang, para sa akin lang, na setup ng mga geosynthetics na kumpara dun sa geotex ka dito. Tapos, kasi sabi niya pwedeng geotextile sa taas at baba diba? Kasi geotextile may butas pa din yan. So, it can seep through. Pero, syempre, calculated naman nila. Nakakalculate naman yung, yung drainage, kung how much yun na-filter, how bad is the chemical that can go through the geotex kapag nag-exit pa siya dito. Kasi, na-filter naman na most of the bad chemicals dito. Baka konti na lang yung magsisip through dito. So, they can calculate naman that. And then, under ng geotex, pwede pa nga maglagay ng mga clay or very fine type of soil. So, syempre, may design naman for that. So, it's okay. So, let's have an example for determining yung flow rate. ng isang geonet. So, determine the flow rate factor of safety of a geonet that is used in a primary leachate collection system above a geomembrane and beneath a sand covering layer in a landfill cell, whose plan view is shown in the following diagram. The geonet delivers its flow to the central perforated header pipe, leading to the down gradient removal sump. The landfill is 35 meters high with a waste unit weight of 13 kilonewton per cubic meter. Okay, saglit. Okay, so ito yung height ng landfill, unit weight ng mga basura. So the geonet being considered has been tested and the results are shown. So similar siya dun sa figure 4.7. Site-specific reduction values will be necessary in order to obtain the allowable flow rate. So reduction factors, yung sa table kanina. The design in flow rate is 30,000 liters per hectare per day. So this will be your, ito yung flow rate na required. Q required mo to. Which was the average landfill collected sa New York noong 2000. Note that this value is very much site-specific with hydrology, type of waste, and liquids management at the site, all being major considerations. So, ano-ano yung mga given? May 35 meter height ka, and then unit weight ng waste. Meron kang figure 4.7. Dito, makukuha yung capacity ng geonet mo, yung flow rate capacity niya. And this is your flow required. And then you need to see yung yung plan ng etong plan ng landfill. So this is the landfill. So ito, yung length niya is 150 meters, and then meron siyang gitnang header pipe. So since nakagitna siya, na-divide niya ang landfill into two, upper and lower part. Next, you need to get yung capacity ni geonet mo, di ba? Kasi nandun si Q allowable mo. Para makuha si Q allowable, that is by getting yung Q ultimate mo. Saan manggagaling yung Q ultimate? Dun sa capacity ni geonet, yung nasa figure 4.7. So let's see figure 4.7. Nandito yung figure 4.7. Nandito yung flow rate, yan ang kailangan natin. Pero paano yung normal stress? To get the normal stress, may drawing mo yung landfill. Ay, teka. Nako-cover siya. Let me erase muna to. So, ano yung normal stress para makuha natin yung flow rate ng geonet natin? So, ito yung landfill. Ang height niya is, say, given pala to, 35 meters. And then, ito yung waste mo. Ang unit weight niyan ay 13 kilonewton. So, meron ka unit ni weight ng basura. So, pwede mong makuha yung pressure due to this waste. That is by, multiply mo yung height, this height, times yung basura mo. So, you get yung pressure or the normal pressure na 455 kilopascal. So, with that, makukuha mo. So, nag-estimate ulit tayo dito. Similar dun sa ginawa natin sa geotextile. So, yung normal stress natin is 455. Oh, we need the gradient. Given naman ng gradient, etong mga gradient, the change in head, diba? So, that is yung slope ng landfill mo. Change ng height or pressure head. Tapos, so, it is 2%. So, that is 0.02. Ito yan, gradient. So, sa 0.02. Wala dito yung 0.02. So, estimate ulit tayo. So, it's 0.02 na gradient is somewhere dito sa baba. And then, yung pressure natin is 455. See, this is 500. So, nandito siya. And then, intersection, project tayo. So, kapag mag-estimate, you just have to be conservative. So, paano ka magiging conservative? Anong estimate? So, at least kunin mo yung minimum niya. Kasi capacity ito eh. So, kapag minimum ang kukunin mo, conservative ka. So, it is estimated to be, yung flow rate dito, estimated to be 0.003 cubic meter per minute per linear meter. So, yun yung Q ultimate natin, no? Yung nakuha natin is dito na lang. Q ultimate, ito, ang nakuha nating capacity ng ating Geonet. So, that is our Q ultimate. Let me sulat dito. Q ultimate 0.003 meter cube per minute linear meter. So, next is Q allowable. So, to get Q allowable, kailangan mong isubject ito sa mga factor of safety, which you can see sa dito. Table 4.2, since gagamitin natin siya sa isang leachate collection, primary. So, we will use factor of safety within this range. So, makikita natin dito na ito ang ginamit ni problem. So, pinakamataas niyang ginamit yung reduction factor na 2.0. This is reduction factor for intrusion. So, baka kasi malalaki yung gravel or mga stones na ginamit, or yung size ng stones is yung size na makakapasok, makaka-intrude easily dun sa apertures ng geonet. Kaya minaksimum niya yung reduction factor niya dun. And then, yung reduction factor niya is least dun sa creep. This reduction factor for creep, siya yung pinakamababa. And then, median lang yung sa reduction factor sa biological and chemical degradation. So, may reason yung pagpili ng Kung gusto mong maging super conservative, i-dose mo silang lahat or yung i-maximum mo silang lahat. Yung dose, maximum. But dito, kinonsider niyang maximum is yung sa intrusion, extrusion. So, ayan, nakuha na yung Q allowable. How about Q required? Ito yung Q allowable. How do we get Q required? May given tayo kanina, di ba, yung Q required? This one. But, check the unit. It is in terms of liter to, and then naka-hectares. And then per day. So, you need to convert this one, and convert this one in units na similar dun sa unit ng Q allowable, which is in meter cube per minute, and then linear length na meter. So, take note, liter is volume, same na with this one, volume. Day is a unit of time, so similar sa minute na unit of time. Pero the problem is, this is in hectare, and the remaining unit is a unit of linear dimension lang. But this one is squared, hectare yan. So pag kinonvert mo yan, m squared yan. But we only need a linear unit na meter. So kasi, we need to multiply pa itong width, itong width ng landfill. So, aling width ang gagamitin? Siyempre, yung critical width. Kung matitingnan ninyo, di ba, may perforated header pipe dito sa gitna. So, it's subdivided yung landfill natin into two parts. itong dito, and then ito. Kasi may kanya-kanyang grade sila. Yung upper part may grade downward pa dito, 2%. And then yung lower part may grade siya papunta kay header pipe. So papunta silang dalawa dito. So na-divide siya sa 2. So yung upper part, iba yung width niya kasi meron siyang inclination na 5 degrees. So this one, hindi mo alam yung length niya. And this one is 25. So, baka mas mahaba to. So, you need to use this kung mas mahaba to. Dahil ito yung critical na width. Mas malaking width siya, diba? So, let's find out ano muna itong distance na to. So, you can get that by SOHCAHTOA since tangent theta is equal to opposite over adjacent. We have angle and we have 150 na given meters dito. Ito. So, 150 itong side na to, yung adjacent side. So, we can get yung x or the opposite side na to. So, substituting tangent 5% equal yung opposite, which is what we need. This is what we need. And then, adjacent side is 150. So, makukuha natin si O, which is equal to, dito natin siya. Dito ko siya kinompute. So, 150 tangent 5 is 13.1. So, pag i-add mo yan dun sa given na 14 meters, it is equal to 27.1. 27.1 is greater than 25. So, ito ang length or the width na mas critical. So, we will use this side, yung 27.1 sa equation. So, ito yung given natin. I-convert natin ang mga units niya, diba? Yung liter, i-convert natin. Yung hectares and day, i-convert. So, makikita nyo dito yung conversion. So, meron tayong 10,000. This one is to convert, This one is to convert yung hectares. And then, this one is to convert yung liter. So, makukuha mo itong given na flow rate, na design flow rate. So, may natira pang days. So, pagdating dito, doon pa lang siya kinonvert. Ito yung mga factors to convert itong day na to into minutes. Ito. And then, di ba naka-squared pa? Ano ba tayo? Okay. Naka-squared pa to. Dapat meters lang to, di ba? Doon na paggagamitan ng 27.1. Itong kinuha natin dito. Because that's the width na most critical sa ating sa landfill natin. So, this one multiplied by 27, and then the rest are just factors to convert yung day na to. So, we get na our Q required in units na similar doon sa Q max natin. Pares na silang cubic, minutes, meter. So, pag dinivide natin silang dalawa, cancel lahat. So, we just get a numerical coefficient which will be our factor of safety. So, substituting yung mga nakuha natin Q allowable and Q required dito sa equation natin ng factor of safety. So, we get 5.1. The factor of safety, of course, acceptable. Lampas siya sa 3. Yan lang. So, that will be our answer. Number 2 example. This is Geonet used in transportation-related application. So, given an area that is to be retrofitted with a new pavement because of past problems with frost heave. Frost heave is the upward movement of soil due to ice formation and growth in frozen ground. So, kapag malamig ang panahon, syempre may tubig-tubig pa din tayo dito. So, pag yan nag-freeze, diba kapag nag-freeze ang water, lumalaki yung volume niya. That's why i-extend yung volume, mag-extend upward, may pressure. It could leads to cracking sa road natin dito sa taas. So, the solution is to drain that water para hindi maapektuhan yung road natin. Imbes na pumunta dito, maapektuhan yung road, ide-drain na yung tubig dito by the Geonet dito. So, sabi nga niya, the new scheme is intended to have a Geonet with thermally bonded geotextile on both sides and will be placed immediately beneath the depth of maximum frost penetration, as shown in the diagram below. Based upon the rising capillary water, the required flow rate to be conveyed is estimated to be 0.17. A candidate geonet has been selected and tests performed at a gradient 0.05 have resulted to a flow rate na ito. Okay, so what is the corresponding factor of safety? So, meron na tayong nakuha na yung flow rate. So, we don't need yung table. This is the flow rate na this will be our Q ultimate na. This is the capacity of our material. So, next, we need to get Q allowable by applying yung mga reduction factors. And then, next na kukunin is yung Q required. Q required is this one. Ito daw yung kailangan na i-drain na water na umaakyat by capillary action ng tubig galing dito. So, capillary. So, gagamitin din natin yun kasi basehan sa pagkuha ng factor of safety or reduction factors natin. If we look at yung table, ito yung table. So, we're going to use yung Geonet for capillary rise ng water. Nasaan capillary breaks. Ito ang gamitin natin. Okay. So, our factor of safety, reduction factor should be within this range. So, nasan tayo? So, ayun na. And then, gradient, take note, it's 0.05. So, as we've said, to get the Q allowable, factor of safety. So, let's check kung itong mga factor of safety na to are within dun sa range. 2132. So, 2132. So, within the range pa siya. So, within the range ito. Okay. So, this one. Gitna. Ito. Ginitna. So, yung median ang kinuha niyang factor of safety. So, okay tayo. That's how we get yung reduction factors, factor of safety. Ayan. So, that's how we get yung mga reduction factors na to doon sa capillary breakage. Dahil yun ang paggagamitan ng ating Geonets. So, multiplying each and then i-divide dito, we get the Q allowable. So, next Q required. So, given na yung Q required. So, eto na yung Q required natin. And checking the units, parehas sila. So, magka-cancel out sila totally. No need for conversions. So, ayun na. Ang makukuha natin is 2.4. So, okay yung factor of safety natin. So, this one, it will be in assignment 2. Ipopost ko sa Canvas ang assignment 2.